Matirosyan. Today we're going to be covering complex numbers in the senior advanced lecture. To start off, we're going to be talking about basically what I is. And so as you can see, it's something that we call an imaginary number, and it represents the square root of -1. And this is important because, for example, when dealing with the square root of 4, right? Square root of 4, it can be either plus or minus 2. Because -2 times -2 is 4, and +2 times +2 is 4 as well. But when we're taking the square root of a negative number, even if we're to multiply a negative number by a negative number, it's still going to end up a positive number. So with the normal real number system we deal with on a daily basis, there is no way to, in theory, get the square root of -4. But with the imaginary number system, we are allowed to get the square root of -4. So the square root of -4, using this new system we're going to be learning today, would be 2i. And just to cover something else quickly while we're on the topic, just 2 by itself is something we call a real number. 2i is something we would call a pure imaginary number. And then let's say we were to deal with a number like 3 plus 5i, this we would call just an imaginary number. So just to cover that again, this we would call a real number, this is something we would call a pure imaginary number, and this is something we would call just an imaginary number. When we're dealing with imaginary numbers graphically, right? Normally, we would have an x-axis going horizontally and a y-axis going vertically. As you can see on this graph, we actually have, instead of a y-axis, we have an imaginary axis. So basically, let's say we were to take the number 3 minus 5i, right? What we would do is we would move over 3 on the x-axis, and it says minus 5i. So this is just basically telling us, okay, we want to go down 5 on the imaginary axis. So 3 this way, and then 1, 2, 3, 4, 5. So this number, 3 minus 5i, would be represented right here, graphically. And so this is important when we start doing stuff like absolute value with imaginary numbers. Okay, so we're going to be doing basic addition, subtraction, multiplication, and division with imaginary numbers now. So here's our first problem. 3 minus 6i plus 5 plus 5i. So just imagine I is like a variable like x, and you're just doing basic addition with variables. So what we would have here, it would be 8 minus 6i plus 5i, that just becomes I. Okay, so it's really simple, really easy stuff, really fun stuff. Let's do, for our second problem, we'll do a subtraction problem now. So we can do 3 minus 6i again. And let's go with like a 7 plus 12i. Spice things up a bit. So, just basic subtractions becomes 3 minus 6i, and we distribute the negative sign to both terms inside the second parentheses. And then, so what is this? 3 minus 7, that becomes -4. And negative 6i minus 12i, that becomes -18i, I think. Assuming I did not do my math incorrectly. And yeah, so now we'll be moving on to addition, we'll be moving on to multiplication and division problems now with imaginary numbers. Okay, so here we have, I basically wrote out what happens when you multiply I by itself, right? So here we have I is equal to the square root of -1, like I covered earlier. When we square I, it becomes you square the square root of -1 by itself, so that just becomes -1. When you multiply it, when you do I to the third, that becomes -I, because you're just taking -1 and multiplying it by this, and this is equal to I. And then when you raise it to the fourth power, it ends up being 1, because -1 times -1 becomes 1. And so when we're given a problem like, let's say I is raised to the 1973, we can, instead of like multiplying I 1973 times, we can just use this repeating pattern to figure out what it's equal to. Because as you can see, I to the fourth is equal to 1, right? So if we go I to the fifth, let's say, well, would you look at that? I to the fifth is just equal to I, because it's 1 times the square root of -1, which is I. So it's just going to equal I again, right? So for example, this problem, if we do 1972 divided by 4, this will become 16, and this will equal to 4, and then 3 comes down, the 7 comes down, the 2 comes down, and what is this, 372 divided by 4? I think that goes in evenly a perfect amount of times, right? Because that's 36, so this becomes 9, this becomes 3, minus 372, so we get 0. So if we know it goes in perfectly 493 times into 1972, and then it's just I is raised to, basically, this just becomes I is raised to 1, and we know I raised to 1 is equal to I. So that's a way you can solve these really hard, complex problems, and those occasionally show up on tests like the ACT or AMC or AIME. And yeah, okay, we'll be going on to division now. Okay, so I noticed I said we're going to go on to division, but first we're going to do a multiplication problem, and then we'll go on to a division problem using imaginary numbers. So once again, like I was saying for addition subtraction, what basically happens is you treat I like a variable, like x, and then you just multiply it out, right? So the way I multiply numbers, because I don't want to put a lot of thinking into it, I just do this. I make a box method personally, and then I just multiply everything out. You can use any method that works for you as long as you understand it. And it gets you the right answer consistently. So we get 12 plus 20i plus 8i squared. Normally, if I was an x, and this was just a variable problem, we would be done, because x squared, you can't really simplify that. But as I just discussed, I squared is actually equal to -1, right? Because, well, we know I is equal to the square root of -1, so the square root of -1 squared, that's just -1 times -1 equals -1. So we can substitute this in, so this becomes 12 plus 20i plus 8 times -1, so this becomes -8, and whoa, look at that, we can simplify it. So this becomes 4 plus 20i, which can also be simplified into 4 plus 1 plus 5i, I think. So that would be your final answer. Or this actually would be your final answer, because I can grade that easier on your guys' quizzes and homework. So just leave like this, please. Okay, for division. Normally with variable numbers, so the problem here is 6 plus 4i over 2 plus 2i, but so variables like x instead of I, we would be able to just do long division or some other way of dividing this. But since it's I, basically we want to be able to simplify this. So the I, it's gone. It's not there anymore. We don't like having imaginary numbers on the new denominator of our fraction. So the way we would solve this problem is using something called the conjugate. Let me spell this out because it's fun. So the conjugate, for example, the conjugate of 2 plus 2i would be 2 minus 2i. So it's just basically, imagine if it's like a plus b times a minus b. This gets you to basically a squared minus b squared. And some of you may already know that because I've covered it before, but the reason this is important is because it lets us do two things. One, it lets us cancel out this 2i, because if we multiply 2 plus 2i times 2 minus 2i, we're going to get like 4 minus 4i squared, and as I just discussed here, I squared equals -1, so we're able to simplify the bottom of this equation pretty quickly. But it also gets rid of these middle terms, right? Because if we had, a plus b squared, what we end up getting as a result from that is something like a squared plus 2ab plus b squared, right? But then this leaves us with an ugly middle term, which, like here, if we were to do 2 plus 2 times 2 plus 2, we would get like 8i in the middle, and we don't want any i's left on the bottom. So that's why we multiply it by its conjugate. Okay, so now let's get back to this problem. So 6 plus 4i, and sorry if this is difficult to see, over 2 plus 2i times the conjugate of the term on the bottom. So that's going to be 2 minus 2i over 2 minus 2i. Okay, let's see. So for the top, sorry this is a diagonal by the way. For the top, we're just going to do something basic like that, right? With 2 minus 2i instead of 2 plus 2i. So our answer is going to be a little bit different. But on the bottom, then it lets us simplify it, which in turn will make the whole problem easier to read. So we're going to get, I'm just going to do some mental math really quickly, which might be wrong, but you know. So that becomes 12, 8i, what is that? Negative 12i, I think. So 8i minus 12i becomes negative 4i. Why do I have a minus sign here? This should be a plus sign. And then minus 8i squared over, as I was saying earlier, this becomes like 4 minus 4i squared. And so now we can simplify this because we know I squared is equal to negative 1. So that becomes positive 8 because it's already a negative 8 times negative 1 is positive 8. And this becomes positive 4 because negative 4 times negative 1 is equal to positive 4. Okay, so that's going to become 20 minus 4i over, what is this, 8, I'm going to say? Yeah. I'm assuming I did my math right. I probably might have done it wrong. I don't know. Maybe you guys can leave a comment and tell me if I did it right or wrong. And then, like we did here where we took out some stuff, we can also take out some stuff here. We can do 20 over 8, which is 10 over 4, which is 2.5. So 2.5 minus 1/2 I. And this would be our final answer. I think 2.5 minus 0.5 I looks much better than this whole combination. And yeah, that's how you deal with division for complex numbers. Now we'll be moving on to the next section. Okay, so now we're going to talk about the different types of ways to represent complex numbers. So the first way I described it earlier on was, I think I used 5 plus 3i or 3 plus 5i or something like that. But basically this is something we call the Cartesian representation. And another way to write this would actually be z is equal to a plus bi. So we can draw some similarities to this, right? So this is actually y equals 5 plus 3. Anyways, so 5 is our a coefficient, right? So basically 5 is equal to a. And then here b is equal to 3. So b represents the coefficient in front of the imaginary number. And yeah, that's basically all we need to really know for this stuff. So this is particularly useful when we're trying to describe the number, or trying to represent the complex number in question. And this also comes in handy when we're trying to find the absolute value of a complex number. So normally, you know, when you're trying to find the absolute value, it's going to be like y equals, I don't know, 5 minus 3, or like 3 minus 5, and these both equal to 2 because you're finding the absolute value. With complex numbers, as you saw in my graph earlier, it looks a bit weird because you have the y-axis going upward and the x-axis going this way. So it's kind of difficult to find the absolute value when you have a number that's also moving vertically instead of just horizontally like with this stuff, right? Because this is using real numbers and this is using imaginary numbers. So find the absolute value for complex numbers, what we end up doing is, this is our formula. AV is equal to the square root of a squared plus b squared. And so this is pretty cool, because basically what this describing is, let me draw a quick graph again, right? So we have 3, what number will I be using? Let's go with 5. Okay, so our number that we'll be doing an example with is 3 plus 5i, right? So we go 3 to the right, and then we go vertically 5. So this is where our point's going to be. So if we want to find the absolute value, this is what this equation is telling us. The absolute value of this number will be this distance between the origin and this point that this number represents on this graph. Yeah, so that's how you find the absolute value. So for this problem, it's going to be AV is equal to the square root of 3 squared plus 5 squared. And so that's equal to what? 9 plus 25, which is equal to the square root of 34? And you can simplify that to like what? No, you can't even simplify that because it becomes 2 times 7. Yeah, you can't simplify that. So this would be your answer for the absolute value of this number. An important note to make is we don't do 5i squared. All we do is we take the coefficient to b, which is, remember, if you're paying attention, that's 3 here, but here it's going to be 5. So all you do is you take the coefficient for each number, and then bada bing, bada boom, you get rad 34. Also, if you notice, this formula is very, very similar to the formula for the Pythagorean Theorem, which is what you learned when you were probably in kindergarten or something, because they teach it at that age now. And so, yeah, that's how you find the absolute value for complex numbers. Alright, so now we're going to be learning about polar coordinates. So, you know, polar, North Pole, polar bear, you know, all that fun stuff. Yeah, we're going to be learning about that now. So here you can see my polar bear. I am proud of it. Do not make fun of me, thank you. So basically, polar coordinates are a way to translate, like for example, my number from last time around. This is what we call an imaginary number. So we can translate this into an equation describing where a point is located on the polar graph, right? So this is one way, but there's also another way, which is more useful for stuff we're going to be learning in a bit. But this is the equation that we use. So it's z, which is just basically equal to the y that we use for normal equations. Z plus z is equal to r times the cosine of theta plus I times the sine of theta, right? So what does this mean? The theta means in our equation, let me draw another graph. So we have 3 plus 5i, right? So this is where the points are located, right? Okay, so what this means is that this angle formed here, it's going to be really small. Here, let me draw it here bigger. This is what this looks like here. This theta, this angle is what we're going to call theta, and that angle is what we're going to plug into here. Also, so remember how I said this is the 3 represents the x-axis and the 5 represents the y-axis, right? So what we can basically do is this becomes 3, this becomes 5, and this number here, normally when we're doing Pythagoras Theorem, we're doing a squared plus b squared equals c squared. Here it's going to be 3 squared plus 5 squared equals r squared, right? Whoa, look at that. So we can find r to put into this equation. And if you remember from the stuff I just talked about, what does r squared also equal? It equals a squared plus b squared. Whoa, look at that. Oh my god. Whoa, wow. Oh my goodness, all the dots are connecting, right? So, this is what the absolute value of here to here, here to here. So that's what r represents in this equation, right? And what does theta represent? It represents this angle right here, which you can figure out by just doing like tan inverse of 5 over 3, and that'll get you your angle value, right? So yeah, and then you just plug in theta here and here, and you plug in r here, and you have your equation, right? So I think that's pretty neat, if you ask me. So also, I just forgot to mention the last section, the absolute value of the length from this point to this point, right, from the origin to the number here. It's called the absolute value, but we also call it the modulus, right? That's just another name for it. So let's do an example, I guess, to help you guys better understand what exactly it is I am talking about. and how useful it is to convert that equation to this equation with the z. I'm not erasing my polar bear because that's actually going to lure. Okay, so we're going to be doing the first example on your packet, which will be 4 plus 3i. And we handpicked these numbers to make it very easy for you guys to understand. So what we'll be doing is, so first we're going to do a mini graph of it because that helps us understand what exactly it is we're dealing with. So 1, 2, 3, 4, and then 1, 2, 3. So this will be our triangle here. So we want to find this value of theta right here, and I'm going to draw it bigger again, so it helps us with our calculations. Okay, so we're gonna go 3 this way, and this is not drawn to scale, by the way, because I cannot do that. And here is our r value. So we want to write this equation in the form of z equals r cosine theta plus I sine theta. Okay, so first things first, we're going to find the value of r. So this is a very basic, simple Pythagoras triangle theorem. So what's this? 9 plus 16, that's equal to 25 equals r squared. That looks like an 8. There we go. Now that looks like a 5. R is equal to 5. Okay, cool. We have the first piece of our equation. So z is equal to 5. And now I want to find the theta of this beautiful triangle, right? So you can use any trigonometric function that you need to help you find it. I'm going to use tan because that's what makes sense to me in my head, because I know if I get r wrong, and if I were to use r in my trigonometric function, and if then that would make my entire answer wrong. But if I use the established values that are clearly given to me, and I just realized, I think I did this wrong. This should be 4 and this should be 3, right? Okay, close call, boys. So what's this gonna be? As I was saying, yeah, if I use 3 and a 4, and if I wrote them correctly, like I just did, as you can see, then I'll know at least to get theta right, and at least I'll get partial credit if I don't get r right. So what do we do? I'll do tan inverse of 3 divided by 4, and so I did this off camera, but that's equal to 37 degrees roughly, right? In the degrees conversion, not the radians conversion. So using all these numbers, we get z to equal 5 cosine 37 plus I sine 37. And so this is just another way of representing this value right here. Yeah, so once again, the 5 represents the distance from here to here, or here to here, and then the 37 just represents the theta distance. Yeah, that's all we have for polar coordinates. Now we're going on to some more complex stuff with this, so stay tuned. Okay, now we'll be learning about De Moivre's theorem. I don't know if this guy is French or Italian or American. Just his theorem, it's not fun, but we have to learn how to do it because it helps us in really complicated equations. So let's say we have a problem, right? It's what, 3 plus, no, the square root of 3, my apologies, plus I is raised to the 9th. This problem sucks because it's telling me, oh, I need to raise this expression and multiply it 9 times by itself. That's going to be hell to do. So luckily, De Moivre came up with an easy solution. Well, I mean, not really easy. It's a pain in the butt, but listen, just stick with me. So remember that z equals r cosine theta plus I sine theta? Yeah, it's going to become really useful right now. So z is equal to, okay, so first let's make a triangle, as we always do, right? So what, it's going to be rad 3 on the bottom, 1 on the top, r right here, so that becomes r squared equals rad 3 squared plus 1 squared. And luckily, our example made it very easy for us because this becomes 3 plus 1, which is equal to 4, so r is equal to 2. Okay, cool. So we know r is going to be 2 here. Now we want to find the theta of this triangle, right? So it's gonna be, I'm gonna use tan again, because if I got r wrong, which I didn't, but if I were to get it wrong, it's better to get the at least partial credit if I use the numbers that were already given to me. So we have tan inverse of 1 over rad 3. And so you would be able to solve this if you knew your trig identities, but just to save some time, we end up learning that theta is equal to 30 degrees. So also for our lesson, bring your calculator, because it's very important to be able to skip these things. Instead of having to memorize them, you can just plug them into your calculator. But you will be expected to know all of these values by the lesson after this one. So we know it's 30 degrees. So we know it's gonna be equal to cosine 30 plus I sine 30. Okay, so we've converted y equals rad 3 plus I into this formula. So Vardan, I can hear you asking, what are we gonna do with this newly found formula? Because, you know, this is cool and all, and it's new stuff for me, but how am I gonna multiply it, or multiply by itself 9 times? Well, you know, the Matirosyan theorem we will now learn. So with this now written like this, we can apply z. So this is the Matirosyan theorem. I know the suspense for it has been great, and all of you have been just wondering what exactly it is. This is me written a bit diagonally. So here we have basically what it's saying is this. Z raised to the nth equals r raised to the nth, parentheses, cosine n times theta plus I sine n times theta. Whoa, would you look at that? We have something raised here, and now we have something raised here, and now we can apply this formula to this, and, you know, combine them and get an answer, which is great, because then we can do the problem. So z raised to the 9th, here actually let me write this a bit down so I don't have to write diagonally the entire time. Z raised to the 9th is equal to 2 raised to the 9th cosine of 9 times 30 plus I sine 9 times 30. Whoa, okay, cool. Now this awesome equation lets us solve this now. So doing all of the math in your calculator or by head, if you're feeling really lucky, you're gonna get the answer of negative 512i. So this z to the 9th, yeah. So this is why the Matirosyan theorem is important, because you can solve ridiculously hard and stupid equations like this by just changing it into this form, which is just basically the same thing equal to this form, and then just applying the Matirosyan theorem right here. Yeah, and see, my polar bear is also really happy that we have this cool, easy trick to do this. Yeah, so now we'll just be covering a few more topics, and this lecture will be done. You guys will be given these lecture notes, which will basically cover everything I've just said. It will also give you a very big special angle tangle, which basically represents, like, it will give you a bunch of trigonometric functions like sine of 30, let's say, which I know is equal to 1/2, but let's say you didn't know that, the table would give it to you. And then that goes for like tan, cotangent, and it gives you like all the special angles that we want to know the values for, because those will be the ones that come up the most frequently. Like, let's say tan 45, that's equal to rad 2 over 2. Yeah, that'll be it. So during the lecture, we'll be covering how to convert more things. We'll be covering more in depth different theorems that can be used when converting complex numbers into this formula, the z cosine theta plus I sine theta. And now we will be covering some very special problems which deal with imaginary numbers and complex numbers, but these are legitimate problems from the AMC 12 and the AIME. So those are very prestigious math competitions that are well renowned across the world, and so I'll be showing you guys how to do a couple of those. So stay tuned. Okay, so here we have an AMC 12 problem. It reads the polynomial f of x equals x to the fourth plus a, which is a real coefficient, x to the third, plus b x squared plus cx plus d, and this polynomial has real coefficients. So the coefficient before x to the fourth is real, so is a, and so is b, and so is c, and so is d. So they're all real numbers. And then the problem also tells us that if we were to plug in 2i into this function, it would equal to 0. And if we were to plug in 2 plus I into this function as well, it would also equal 0. And so the problem is asking us, what is a plus c plus b plus a plus b plus c plus d? So the way to solve this, well, pause the video and see if you can solve it on your own without me telling you the answer. Because if you can, you'll get 100% on this upcoming test. So pause. Okay, so this is how you solve it. So we know it says x to the fourth, right? So we know it's gonna, when it says x to the fourth, we know it's a fourth degree polynomial. So this means it's gonna have 4 separate roots, right? So basically what we can do is we can write out this equation to basically be like this. If we know 2i and then 2 plus I are roots of it, then we can use that to our advantage. So we write the equation like this: x minus 2 plus I times x minus 2 minus I times x minus 2i, and then x plus 2i is equal to 0. And we can do this because we know these and this are the roots, and we can plug it into this equation. And so after doing that, what we can then do is we can then do x squared. We basically multiply this out and separate it a bit. So it becomes x squared minus 4x plus 5 times x squared plus 4 is equal to 0. So this is just a way of rewriting this. And then if we multiply this out a bit more, well, what would you know? This becomes x to the fourth minus 4x to the third plus 9x squared minus 16x plus 20. Okay, cool. And this is all equal to 0. Now, this equation, it should look similar to this equation, the one they gave us in the problem. So what do? Well, we can realize that 4 here is equal to the a up here, and the 9 here is equal to the b, and the negative 16 is equal to the c, and the positive 20 is equal to the d. So a plus b plus c plus d, you just add up the coefficients, right? So negative 4 plus 9 minus 16 plus 20, that gives us an answer of 9. So this is an example of an AMC 12 problem. Now we'll be moving on to an AIME problem. Okay, so now we'll be doing an AIME problem, which is a very difficult math competition. So it states that A, B, C, and D are integers. I'm sorry, there is no D. There's only A, B, and C in this problem. And we know that C is equal to A plus BI to the third minus 107i, and they want us to find C. So the way we can do this is basically we expand this. So C is equal to A to the third minus 3ab squared, but then parentheses plus 3a squared b plus, minus b to the third times I. And so basically, oh, and then minus 107. What we can do is we can move the 107 to the other side. 107i, my bad. So this becomes 107i plus c equals this thing. And so if you'll notice, 107i, 3a squared would be minus beta third I, and then c, which is an integer, is equal to this. So we can separate this equation out into two separate equations. 107i is equal to 3a squared b minus b to the third I, and then c is equal to a to the third minus 3ab squared. So we now have two separate equations. So what we can do is we can solve for this equation, right? So we basically do 107 equals, we divide by I from both sides to begin with. So 3a squared minus b to the third. So basically, b can either equal 1 or 107 due to the way that this equation ends up working out. And we know that because both 1 and 107 are prime numbers, and if it's raised to the third, then we know it's a prime number. Anyways, I'll explain it more in depth during class, but just know that it can either be 1 or 107. So if it were to be 107, then it actually ends up not being 107 due to the fact that if you substitute in 107, you end up getting like 3a squared equals like 107 to the third, and if you multiply that out, it ends up not being possible for a to be an integer, which is what it was stated in the beginning. So b cannot equal 107, instead b has to equal 1. When b equals 1, we end up getting 3a squared is equal to 108, because b to the third is 1, so you add 1 to each side and you get 3a squared equals 108. And then you solve for a to equal to 6, and then once you know what a is, you can solve for b, and b ends up being, if I recall, like 3, I want to say. So then you plug it back into this equation when we split it up, and so if we know a is 6 and b is equal to 3, then c is going to be equal to 6 to the third minus 3, what is this? 3 times 6, and this ends up equaling to 198. So this is how you would solve this problem, and this is like a really basic AMIE problem. So, and this was already pretty hard because I don't think I did that great of a job explaining it. I'll explain it much better during class time, but just know that this is an example of an AIME problem. Alright, that's it for today's lecture on complex numbers. Thank you very much for watching, and make sure to bring a calculator to next lesson because as you saw, it's going to be a lot of complex trigonometry, and I'd rather you guys have a calculator and be able to solve those problems relatively quickly so we can move on to the more interesting and complex stuff. And yeah, make sure to like and subscribe, and thanks for watching.
Don't forget to subscribe and like. If you have any questions, you can email info@agoramatrico.org or comment below and we'll reply back. Maybe. And if you want to see practice things or anything about us, you can visit our website, which is basically the end of the email but without the info and the end. So bye!